So much of our life happens online now, but how do we actually trust any of it? How do we know who we're really talking to, or that a file we just downloaded is the real deal? Well, today, we're going to pull back the curtain on the really clever system that makes all of that digital trust possible. It's like a digital handshake. Think about it in the real world. It's pretty simple, right? You sign a contract, and that squiggly line of ink is your unique mark. It's your proof. But what happens when that contract is just a file on a computer? There's no paper, no ink, just a long stream of ones and zeros. How do you sign that? And yeah, that is the central question, isn't it? How can you be absolutely sure who sent a digital message? And maybe even more importantly, how do you know that nobody messed with it on its way to you? How do we create a digital signature that's just as rock solid as a real one? While there's a fancy term for this, it's called non-repudiation. It's really just a technical way of saying that you can't back out later and say, nope, wasn't me. I never sent that. And to get to that level of certainty, we basically have to solve two big problems. We have to prove what the message is and who it came from. So let's start with the first one, data integrity. We need a bulletproof way to know that the file we just got is the exact same file that was sent. No changes, no deletions, not even a single comma added. And the amazing cryptographic tool we use for this is called hashing. A hashing algorithm is a bit like a magic blender. You can throw in any amount of data, a single word, an entire encyclopedia, and it spits out a short, totally unique string of text. The best way to think about it is as a digital fingerprint. Okay, let's see how this actually works. Let's say we take a huge chunk of data, like a whole digital encyclopedia, all 8.1 megabytes of it. We run it through one of these hashing algorithms, and out pops its unique digital fingerprint, a string of characters that represents that entire book. Now here's where the magic really happens. This is what makes hashing so powerful. Look at this. We go back into that massive file and we change just one single character. Maybe we fix a typo or add a period. Then we run it through the hashing machine again. And bam, the new fingerprint is completely, totally different. It's not just a little bit different, it's unrecognizable. Yeah, this quote just nails it. It really is like a fingerprint. If the data changes in any way, no matter how small, the fingerprint becomes something else entirely. And that is how we prove that the data hasn't been tampered with. Okay, great. So hashing is fantastic. We know the message we received is the right one. It's got integrity. But it doesn't tell us a thing about who actually sent it. So we've solved the what part of the problem, but we still have to figure out the who. And this brings us to the second piece of our digital trust puzzle, sender origin. Now we need a way to mathematically prove who the message came from. This is where the digital signature comes into play. It's a brilliant technique that actually combines both of the proofs we need. It uses a clever little system called a public and private key pair to lock in both the sender's identity and the message's integrity. The idea behind it is actually pretty elegant. Everyone gets two keys that are mathematically linked together. You get a private key, which you keep completely secret. You never ever share it with anyone. This is what you use to sign things. Then you have a public key, which you can give out to everybody. People use that key to verify your signature. All right, so we have our two main ingredients, right? We've got hashing to check the what, and we've got digital signatures with public and private keys to check the who. So now let's put it all together and see how it works in a classic scenario with our good friends Alice and Bob. So just a super quick recap of our toolkit before we dive in. For data integrity, the what, we're using hashing. And for sender origin, the who, we're using digital signatures and those keys. Got it? Okay, let's see this thing in action. So here's the setup. Alice needs to send a really important message to Bob. It says, "You're hired, Bob." She absolutely has to make sure that Bob knows it really truly came from her and that it wasn't sneakily changed along the way to say something like, "You're fired, Bob." The stakes are high. Okay, so here's exactly what Alice does. First, she takes her message and hashes it to create that unique digital fingerprint. Second, and this is the most important step, she uses her own private key to encrypt that fingerprint. This little encrypted bundle of data, that is the digital signature. Finally, she attaches this signature to her original message and sends both of them off to Bob. All right, the message lands in Bob's inbox. Now it's his turn. He's got two things, the original message and that digital signature. So first, he takes Alice's public key, which she gave him earlier, and uses it to decrypt the signature. That reveals the original fingerprint Alice sent. Second, he takes the message text he received and runs it through the exact same hashing algorithm to create his own brand new fingerprint. And now for the moment of truth. He compares the two, the one he decrypted and the one he just made. If those two digital fingerprints are absolutely identical, then it's a success. We're golden.
So let's just pause and think about what this little dance actually proved. First, we proved integrity. Because the hashes match, we know the message wasn't changed one bit. Second, we proved origin. That signature could only be decrypted with Alice's public key, which means it had to have been created with her secret private key. And when you put those two things together, you get the grand prize, non-repudiation. There is no way Alice can deny sending that message.
Now, I know that process might sound a little complex, but the real beauty of it, the absolute magic, is how seamlessly it all works in our actual lives. So let's bring this back to why any of this really matters to you. That whole process we just walked through, the hashing, the encrypting, the sending, the decrypting, and the comparing, all of that usually happens in the blink of an eye, completely invisible to you. It's often triggered by something as simple as you clicking a single button that says send or sign. And that's really the big takeaway here. Non-repudiation might sound like some boring technical jargon, but it's not. It is a fundamental pillar of modern security. It's the bedrock of digital trust. It's what lets you do your banking online, sign a mortgage from your living room, and trust that a software update is actually from the right company. It's the invisible handshake that secures our entire digital world. So I'll leave you with this thought. Now that you know how this digital handshake actually works, start looking for it. It's happening all the time, completely unseen. It's in your secure emails, your App Store downloads, every time you see that little padlock in your browser. The more you look for it, the more you'll see this really elegant system of trust working silently all around you.